Speakers, myself, Kyle Bradbury, Assistant Research Professor in Electrical and Computer Engineering, and Jordan Maloff, who's also an Assistant Research Professor in Electrical and Computer Engineering. And we'll first start off by talking a little bit about unsupervised learning. It's, computer vision. It's what it is, what applications related to energy may be of interest, and some resources that you can jump into for learning more about it. Okay. So first of all, what is this computer vision thing that we talk about? Well, first, before we talk about computer vision, we have to briefly introduce some of the basic concepts here. So first of all, if you were given a picture of these two flowers, how would you go about telling them apart? Right. So you might look at this and say, well, okay, we've got, the sepals and the petals are shaped a little bit differently. They might have different lengths, different widths. The coloration might be a little bit different. There are a lot of descriptors that we might look at these flowers and think, okay, yeah, these might be some good characteristics to distinguish this Iris setosa from this Iris virginica. And we call these features in machine learning and computer vision parlance. So features are descriptors, quantifiable descriptors of an object of interest. And so with that, we are taking what are just arrays of pixels here and converting them into a number: pixel, sepal width, sepal length, petal width, petal length, right? So we can take that and we can plot each flower as an individual point in what's known as feature space, just a plot of our different characteristics along the x-axis and y-axis here of the plant. And we can see that, the setosa, tends to have different characteristics than virginica and versicolor in terms of sepal length and sepal width, but there's some stronger similarity between versicolor and virginica. So if we were just trying to classify setosa, we could say, okay, well, we take our image, we measure these different characteristics within the image, and we put a decision boundary, and everything above it is setosa, everything below it is versicolor or virginica. Now, this basic idea of either classifying things or creating estimates of quantities, if we want to say how old is this flower, that'd be a regression problem. The type of flower is a classification problem. There are a number of types of problems that we can address when we try to go from image into information, right? And so in the computer vision space, there are three types of problems we're typically looking at. The first is scene classification or image classification, taking an image and saying, is this a residential scene, a commercial scene, a forest, a desert, a body of water, right? Which of these is most likely to be the case here? And we pick the one that's most likely, and we move forward with that. Okay, so this is what you most commonly see when you encounter computer vision problems, but it's not the only way that this is done. Another is object detection. Okay, so you can take an image and maybe you want to find each of the individual buildings and cars in an image, all the different pieces, and this yields a slightly different methodology for achieving this goal. And then a third problem is image segmentation. We take that picture and we want to break it pixel by pixel into what it is, whether it's road or sidewalk, plants or water, whatever it may be. And you can assign for each of those relative probabilities to all of that. These are our kind of three big bucket categories when we start to look at computer vision for image analysis. So, what naturally comes up there is, there are there isn't just one approach to each of these. There are many approaches, many different algorithms that we can use for each of these. And so with all of this, we want to start thinking, how can we take some of these principles? How have they been used for energy systems applications in the past? Well, turns out they've been used in a lot of different settings, especially in the last decade or so. So, what are some examples? Well, estimating solar energy generated using different types of remote sensing data, whether it's solar irradiance data or a combination of imagery data. You can use that to make predictions about how much solar energy will reach the surface of the Earth at a given point in time. More traditional fuel sources, you have things like coal, oil, and gas with coal mine monitoring and change detection, seeing how things are growing over time, detecting oil wells, identifying refineries, storage tanks, oil tankers. All of this, we can identify a lot of this with satellite imagery. Additionally, some of the smaller scale or more distributed generation infrastructure like solar PV we can do as well. You look at some of Ben's work in this space. He's looking at that with drones. But with all of these, what we're doing is we're applying some combination of those techniques. Here we're doing an object detection type processes. And for something like this, it might be more of a image segmentation process here. Whereas here, if we were inspecting turbine blades for visible defects, that might be a classification problem, or all of these things. So there are many problems in the space that have been addressed with this, from transmission line identification and insulator monitoring, the quality of the health of that insulator, to building energy consumption estimation and electricity access and reliability estimation. Lots of different approaches, all relying on these fundamental computer vision techniques as applied to remote sensing data. And a number of folks around this table, Jordan, myself, and Leslie, have also worked in this space. And some examples of some of the work that we've done. One here is solar PV identification. Well, we've taken a satellite image, used computer vision to identify the solar panel, then map that through a regression to estimate power capacity of that solar panel, and combine that with how much sun hits the solar panel to estimate electricity that's generated. So we can take this, identify our individual solar panels in imagery, and then develop larger scale estimates of where those solar PV arrays exist, and potentially say how much energy they produce. Right. Another example of some of the work that we've done in this space has been around building energy estimation. So take another input image. We segment the buildings. We determine whether they're a commercial or residential. Again, all of these processes using computer vision techniques, and then extract features from the data. Instead of petal width and petal length, it might be building area, building roof coloration, and things of that nature to give us features, predictors that we can then use to estimate the energy that's been produced by this. And I'll share one other application, which is not from our team, but I think is really interesting. It's on large scale infrastructure and poverty estimation. And so this team of researchers did something pretty interesting. Stefano Erman and David LaBelle out in Stanford, and they took satellite imagery of a landscape, and then they took the corresponding nighttime light data, Earth at night type information. And what they did, they trained an algorithm to take this input image and learn to predict from these visual features the nighttime light information. And you might think, well, why would you want to do that? Well, turns out that the information that is required, that is developed as we estimate some of these try to estimate the nighttime lights, it actually develops features that are rich in information about other types of infrastructure and demographics. So, here's 4 examples of some of the features that were developed. Well, this one, you can see where these features were highly activated over these regions. And it tends to be in areas where there's a lot of urban activity. If you look here, what does this look like? Oh, well, it tends to be activated in areas where there's a lot of water. So what they found was that by training on these nighttime light bits of information, they were actually able to learn about other types of infrastructure and then use this information to predict things like the presence of sewage, electricity, and piped water in different parts of Africa. So very cool, highly extensible technique that can be used in this space. So with all of this, what are the tools that we need, and how do you get started working in this space? Well, really, we've seen over the last decade tremendous growth in computer vision and pattern recognition technologies. There's a competition called ImageNet that's been held annually. And what you see is back in 2010, before deep learning techniques emerged, you can see the percentage of error that was made in these competitions. Each year, you see them getting a little bit better until in 2012, there was a major advance. And this was the first application of a deep learning technique to this. And from then on, the deep learning techniques dominated. And in this particular application, they've actually become superior to human results for this competition. But how did this end up? What is this all based on? Well, a lot of it's based on what's known as convolutional neural networks. What should be known about these is, unlike what we talked about with the flower example before, where we were thinking, we have to measure this petal width and petal length and sepal width and sepal length and extract our features manually, convolutional networks and deep learning techniques automatically generate informative features for the problem at hand. That's the magic sauce behind these techniques. So, they automatically extract those features for what we're doing. But to do this, it requires significant computational resources, particularly GPUs, graphics processing units. Now, these systems, and NVIDIA has a bunch of these cards, Google has tensor processing units now. These are the workhorses behind this these advances. And to access these resources, we need access to these GPUs and TPUs. And so there are some things that you can start using now. There's a free option called Colab that you can use for some of this work. And there are a number of paid options in this space to give yourself access to it. Your respective institution may also have access to GPUs. For those at Duke, we do have some GPU servers available if there are such needs, and we can connect you with folks to help explore those options. So this is one thing that is important. The other is kind of the software that helps make the magic happen with all of these algorithms, and these are typically deep learning frameworks, things like TensorFlow, PyTorch, or wrappers for TensorFlow like Keras that make it a little bit easier to code. So you probably have to be familiar with some form of these to be able to use some of these techniques, and have a development environment that that you're comfortable in, whether it's VS Code or Jupyter Notebooks, Spider, or PyCharm. There are a number of considerations there. The other thing that you may want to think about is what data sources you have to use to bring to your problem. So, we are in a good point in time now where there are many freely available satellite resources and remote sensing resources, especially Landsat and Sentinel. But these are fairly, low resolution, 10 meters per pixel or 15 meters per pixel. And there are much higher resolution satellites getting up to, 30 centimeters per pixel. But sometimes these can be a bit expensive. So that's the only downside. But there are often opportunities for researchers to access these data at no or low cost for smaller areas of interest. And a company called Planet, with their SkySat and other constellations, have actually been able to revisit and re-image the Earth many times. Sometimes, once a day. Sometimes, at that level of frequency, which can be really useful for time change evaluation. So if you're looking to get started with some of this, there are a number of resources that you may want to consider. Introductory texts on this. Introduction to Statistical Learning is a great basic primer on machine learning. And when you're ready, you can kind of jump into some of the deep learning and computer vision texts. This is a great deep learning book on the theory, and these are some really good applied books to help you kind of get started there. Of course, there are many online tutorials. There are courses at a number at Duke that may be of interest if this is a topic of interest, and a number of online courses that may be helpful. I especially recommend these three here: Stanford's CNN course, Michigan's Deep Learning for Computer Vision, taught by Justin Johnson. He does a great job with that. And Berkeley's Full Stack Deep Learning, which is more applied, but gets your hands dirty in the code very, very quickly. So I think a good option too for those who are just jumping in.